Today, we're exploring forces that shape our planet, and specifically one that's quietly messing with the clock we all live by.
Right. It's one of those things you just assume is constant, isn't it? A 24-hour day.
Exactly. But you asked us to dig into this, and it turns out Earth's day isn't fixed at all. It's changing subtly, but, well, relentlessly over vast stretches of time.
It really does shift your perspective on time itself. For us today, yeah, a day is a day, but the planet itself, it's locked in this huge cosmic dance, and we can actually measure it.
And the partner leading this particular change, our closest neighbor, the moon.
That's the one. It's involved in something called a tidal breaking. Sounds quite dramatic.
It does. One source we looked at called it stealing energy from Earth's spin, which I kind of like. It's slow, it's majestic, but it's definitely happening.
So our mission for this deep dive is to unpack that. How does this energy theft actually work? What's the physics behind it?
And what does it mean for Earth, for the moon, and maybe even for the history of life?
Yeah, the consequences are surprisingly far-reaching. So where should we start? The visible effect, maybe?
Let's do that. Okay, so we all see the tides,
Yeah.
right? The ocean's rising and falling. We know it's the moon's gravity pulling on the water.
Mostly, yeah. The sun plays a role too, but the moon's influence is much stronger because it's so much closer. But it's not just a simple pull.
It's stronger on the side facing the moon.
Exactly. The pull isn't uniform across the whole planet. That difference, that gravitational gradient, is key. It pulls hardest on the water nearest the moon, creating one big bulge.
Okay, one bulge makes sense, but we get high tides on the opposite side of Earth, too. What's causing that second bulge? It's further away, so the pull is weaker there.
Right, and that's the slightly less intuitive part. It's basically inertia. The moon is pulling on the solid Earth, the rock beneath the oceans, more strongly than it's pulling on the water on the far side.
Ah, so the Earth itself gets pulled towards the moon, kind of leaving the water on the far side behind.
You got it. So you end up with this slightly squashed football shape, two bulges, one from the direct pull, one from inertia, from being left behind.
Okay, I'm with you on the two bulges, but how does that slow the Earth down? The bulges are there, the moon is there.
It's because the Earth is spinning really fast underneath those bulges, once every 24 hours, roughly, while the bulges themselves are sort of trying to stay pointed towards the moon.
So the planet is rotating, but the bulges lag slightly, or no, wait, which way is it?
The Earth spins faster than the moon orbits. So because of that spin and the friction between the moving water and the seabed, the Earth effectively drags those huge water bulges slightly ahead of the moon's position in the sky.
Ahead. Okay, so the bulges are leading the moon, like they're slightly out in front.
Yeah, exactly. Think of it like trying to spin something heavy that's also being pulled back. The Earth is rotating, dragging these bulges, and the moon, slightly behind them, is constantly pulling back gravitationally, trying to yank them back into line.
And that continuous backward tug acts like a brake.
That's the braking mechanism. It's a constant, gentle, but massive gravitational drag on those offset bulges.
Where does the actual friction happen? Is it just the water sloshing around?
Well, the main energy loss, the real conversion, happens where the water interacts with the solid Earth. So think shallow seas, continental shelves, narrow channels where the water is forced to move against the bottom.
Like dragging something heavy across the raw surface, the friction is at a point of contact.
Precisely. And that friction does two things. It generates a tiny bit of heat in the oceans, but much more importantly, it transfers energy, rotational energy from Earth.
The energy making our day 24 hours long.
Right, that gets transferred into the moon's orbit.
Okay, so Earth slows down. Energy has to go somewhere, conservation of energy and all that. So it goes into the moon's orbit. What does that do to the moon?
It leads to these two measurable consequences. One, Earth's rotation slows, where our days get longer, incrementally but measurably longer.
And two,
And two, that extra energy pushes the moon. It nudges it slightly farther away from Earth into a higher orbit.
further away. Hang on. If you add energy to something orbiting, shouldn't it speed up? Like pushing a swing harder makes it go faster. Why does moving the moon away make it slow down? That feels backwards.
Yeah, it is one of those slightly mind-bending things about orbital mechanics. You're right, we are adding energy, and that energy increases the size of the orbit, the altitude.
Yeah.
But in gravity wells like this, governed by Kepler's laws, when something moves to a higher, larger orbit, its orbital speed actually decreases. It has a longer path to travel, and it doesn't need to go as fast to counteract gravity at that greater distance.
It's like moving to a slower lane on a bigger highway.
Kind of, yeah. It's trading speed for altitude, so the net result, Earth spins slower, the moon orbits higher and slower.
And you said this is measurable. How fast is the moon actually moving away?
The measurements are incredibly precise. It's moving away at about 3.8 centimeters. That's roughly 1.5 inches per year.
Wow, 1.5 inches a year. That sounds
Yeah.
tiny. Almost nothing across all that distance to the moon.
It is tiny year to year, but this isn't just a theory. We know this is happening.
How on earth do you measure a 1.5 inch change over, what, nearly 250,000 miles?
This is where it gets really cool. It involves lasers
Yeah.
and astronauts.
Astronauts.
Apollo.
Yep. Lunar Laser Ranging Experiments, or LLR. During the Apollo missions, 11, 14, and 15, and also a couple of Soviet robotic missions, they left special reflectors on the moon's surface.
Mirrors. They left mirrors on the moon.
Basically, yeah.
Yeah.
Retroreflectors. They're designed to bounce light directly back towards its source with minimal scattering.
Okay. So what do we do with these mirrors?
Scientists here on Earth fire powerful, very short pulses of laser light at these specific reflectors. Then they use incredibly sensitive detectors and atomic clocks to measure the exact time it takes for that light pulse to travel to the moon and bounce back.
Which is only a couple of seconds, right, for the round trip?
Mm.
Just about 2.5 seconds, yeah. And because we know the speed of light very precisely, measuring that round trip time lets them calculate the Earth-Moon distance with astonishing accuracy, down to the centimeter level.
Centimeter accuracy over that distance. Measuring a change of just a few centimeters per year, that's phenomenal.
It really is. It's this constant monitoring year after year, decade after decade, that confirms the moon is indeed drifting away at that 1.5 inches per year rate. It proves the physics of tidal braking is real and ongoing.
So it's slow, but it's relentless. And it's been happening for a very, very long time.
Billions of years. The effect day to day is absolutely imperceptible to us, of course, but over geological time, it adds up significantly.
Let's talk about that geological time. If the Earth has been slowing down for eons, what was a day like way back when, say, when the dinosaurs were around?
Well, scientists can actually look for clues in ancient fossils. Things like certain types of corals or shellfish lay down daily and seasonal growth rings, a bit like tree rings.
And those rings record the number of days in a year back then.
Exactly. By studying these paleoclocks, they've estimated that hundreds of millions of years ago, say back in the Devonian period, long before the dinosaurs, a day on Earth was only around 22 hours long.
22 hours. So we've gained roughly 2 hours on our day since then, thanks to the moon putting the brakes on.
That's the calculation, yeah. The Earth was spinning considerably faster.
Which brings us to the big question, I guess, the so what? Why does it matter if the Earth spun faster millions of years ago? What does this invisible braking really mean for the planet?
Oh, it matters hugely. The speed of a planet's rotation has profound effects on its climate and its overall dynamics, primarily through something called the Coriolis effect.
Right, the Coriolis effect. That's the thing that makes storms spin and ocean currents curve.
That's the one. It's an apparent force caused by the planet's rotation. Imagine trying to roll a ball straight across a spinning playground merry-go-round. From your perspective on the merry-go-round, the ball seems to curve sideways.
And the faster it spins, the stronger that curving effect.
Exactly. So a 22-hour day means Earth was spinning faster, which means the Coriolis effect was significantly stronger back then.
What would that have looked like?
You'd be looking at drastically different weather patterns, probably much stronger winds, maybe more intense storms. Ocean currents would have flowed differently, likely deflected more sharply. It changes how heat is distributed around the planet, fundamentally alters the climate system.
Wow. So it's not just about the length of the day, it's about the fundamental behavior of the atmosphere and oceans.
And that, of course, impacts life. Think about biological rhythms, sleep cycles, reproductive cycles, migration patterns. Everything that relies on the day-night cycle would have evolved under a faster 22-hour rhythm.
It really shows how interconnected everything is. The moon's gravity, the ocean tides, the planet's spin, the climate, the evolution of life. It's all tied together.
Absolutely. Understanding this process, this tidal breaking, helps us piece together the deep history of Earth, how it evolved physically. It shows these, intricate celestial mechanics playing out over billions of years.
It's amazing that such a subtle force, that tiny drag, applied consistently over such vast timescales, can literally reshape the planet's behavior and, well, influence life itself.
It's a beautiful demonstration of physics in action on a grand scale, a continuous, measurable transfer of energy happening right now across space.
So, next time you look up at the moon, maybe think of it not just as a light in the sky, but as part of this slow, majestic dance, this cosmic brake pad that's constantly gently lengthening our day and pushing itself a tiny bit further away.
It's quite a thought, isn't it? That continuous quiet interaction shaping our world.
It really is. Which leads us to our final thought for you, the listener, to mull over.
Ah, yes, the look ahead.
If this subtle tidal friction has already added 2 hours to our day over geological time, changing our climate systems along the way, what might the continued slowing mean? As the Earth keeps slowing down, fractions of a second per century, and the Coriolis effect presumably weakens further, what could that imply for climate, for weather patterns, for life, millions of years into the future?
What does the very long game look like? Something to ponder.
Definitely something to keep wondering about. We'll see you next time.